Hello, everyone. My name is Eleonora Isotta, and I'm a Marie Curie Fellow at the Max Planck Institute for Sustainable Materials. And today I would like to tell you about our our recent published work called Probing Grain Boundary Structure, Chemistry, and Transitions that was published on MRS Bulletin very recently. You can find here the QR code that links to the article itself. And this presentation was also recently given at the MRS Bulletin webinar on grain boundary defect phases, thermodynamics, atomic structure, and properties. Okay, so when we think about grain boundaries, we have come to the understanding that they can behave as phases. So what do I mean? So the idea of grain boundaries behaving as interfacial phases actually dates back to the 70s, when Hart first proposed that according to some thermodynamic conditions, for example, pressure or temperature, then the grain boundary could undergo transitions from, for example, one phase to an additional phase. And over the years, this has been actually proven and demonstrated. And especially after the 2000s, these type of studies have become more and more frequent. And the terminology complexion has been established to refer to grain boundary phases, or sometimes they're called defect phases. And basically, the grain boundaries is really treated as an interfacial phase with its own thermodynamic equilibrium that is being controlled by thermodynamic parameters, for example, temperature, pressure, or chemical potential, so the composition of the bulk material. And this is, for example, one case study where complexions were studied in alumina, and it was really identified the formation of different types of complexions, which was recognized as one of the causes of the abnormal grain growth that happened in the material, with the idea being that the presence of some type of complexions was actually leading to this grain growth because their structure and chemistry was promoting a faster mobility of the boundary, thus causing the abnormal grain growth. And really, the key idea here is that being able to control the boundary phase via thermodynamics leads the way to the development of phase diagrams, where really, based on the thermodynamic conditions, we could predict the specific grain boundary phase that forms. Okay, so we have seen what grain boundary phases are. Now let's see how to observe them, how to observe grain boundary phases and the transitions between them by using high resolution methods. So when we want to use high resolution methods, we typically start by identifying a suitable grain boundaries by using lower resolution methods, for example, SEM imaging or EBSD, electron backscatter diffraction, that allow measuring, let's say, a large area of our samples. And when the ideal boundaries is identified, we can proceed with cutting a lamella. And when we think about the choice of the boundary, there could be several reasons why we select a particular one. For example, one could be chosen because the two adjacent grains have a common zone axis, which leads to, let's say, easier conditions for achieving atomic resolution imaging. Or it could be that we select a specific boundaries because we have informations from other measurements, for example, that boundary is interesting, or we want to correlate the structure and the chemistry with, for example, properties that were previously measured. So when the boundary is identified, we proceed with preparing a lamella for TM observations using focused ion beam. So this technique basically allows to carve a shape into our sample, and a lamella can be extracted and thinned down until it reaches electron transparency. And after this, the TM observation can be carried out with STEM or high resolution TEM mode that allows achieving very high resolution if the lamella is properly prepared. This allows to really detect and infer the atomic arrangement that develops at the boundary. Another thing that we can characterize in high resolution is the chemistry of the grain boundary, and this can be done by using energy dispersive spectroscopy in STEM mode, also on a lamella. Alternatively, one can use electron energy loss spectroscopy. Another method for achieving high chemical resolution is atom probe tomography. This requires the preparation of a different type of specimen, which has a tip shape like this, but allows very high sensitivity and very high spatial resolution. And once we have identified the chemical changes that happen at the boundary, one convenient analysis tool is the Gibson interfacial excess of solute. So a common thing that occurs is that a different chemical composition happens at the boundary. And the Gibson interfacial excess of solute is a method to basically assign what is the composition of the boundary without being too much affected by things like instrumental resolutions or the tilt of the boundary that could also broaden the signal without the signal not necessarily be actually broadened. And the way to proceed is to take the concentration profile and calculate the excess of solute by basically integrating the excess concentration, so the local concentration minus the grain concentration. And with this being done, one can really have the excess of solute for all the species that appear at the boundary. And okay, so let's now dive into some type of grain boundary transitions. So we've seen that we have this grain boundary phases, and we also have spoken that these can transition when thermodynamic conditions change. So let's now see some of these transitions and how they can develop and what could we expect actually with these transitions. So one of the first kind of transitions that were characterized are faceting-defaceting transitions. And these ones are can also be called incongruent transitions because they basically involved a rearrangement of the morphology of the, let's say, global interface morphology. This is work where faceting and defaceting transitions were characterized in copper grain boundaries. And it was observed that when copper was alloyed with a little bit of bismuth, it was forming this faceted boundary. And then when the exact same boundaries was annealed in vacuum to remove some of this bismuth, the morphology completely changed and became a planar interfacial morphology. The very interesting thing that actually proves the transition nature of these boundaries is that when the bismuth was reintroduced with an additional subsequent thermal treatment, the boundary took on again the faceted morphology. And here is another example of such faceting-defaceting transitions happening in aluminum grain boundaries, where as a function of temperature, the same grain boundary also went from faceted to a defaceted back to a faceted configuration upon increase and then reduction of the temperature. Okay, so we've seen incongruent transitions, so again, change of the global morphology, but we can also have congruent transitions, and these have become more and more reported in the last years. So congruent transitions basically imply a change in the grain boundary arrangement of the atoms, but without any change in the macroscopic shape of the interface. And we can see one of such examples for copper grain boundaries here, where it was observed a coexistence of two types of structural units, a domino structure and a pearl structure happening at the same boundary. You can see here a little bit of a simulation of the same boundaries. And basically the coexistence is also a proof of the presence of a transitions, where in this particular work, it was reported that according to the tensional state of the boundary, one would happen to prevail over the other. And the interesting thing about congruent transitions is that we typically we see this change in the structural units. And I mean, of course, with TEM, we see a two-dimensional projection of what happens in reality. So we need to keep in mind that these structural units are actually three-dimensional. And it is, of course, difficult to reconstruct a three-dimensional unit, but this can be done with a combination of atomistic simulations and then image simulation and the TEM, of course, TEM observations. Okay, let's now see another type of transitions. These were also reported, let's say, fairly early in the literature. And these are examples of chemical segregations. And basically, the idea is that in certain compounds, for example, alloys or ceramics, the grain boundary could actually take a different chemical compositions. And this could also be caused by the fact that the boundary has a significantly different melting temperature than the bulk phase. And this is called pre-melting. And in such conditions, the grain boundary basically forms what is called an intergranular film with a different composition. There have been observations of these intergranular films in very different compounds, with also some studies trying to predict and identify the thickness of the films that should form. The last type of transitions that I would like to discuss is chemically driven transitions in the structural units. And basically, the basic idea behind all of this is that when we have a solute atom that tends to segregate at the grain boundary, if this atom has a different valence or a different size, then it is easy that the bonding arrangement will change at the boundary, thus promoting the transition in the structural unit. And among examples in the literature of chemistry-driven structural transition is this one here on magnesium grain boundaries, where it was identified that without gallium, the grain boundaries tend to show a tetrahedron structural unit, as you can see here. But then upon the introduction of gallium, there's a progressive transition to a different structural units, namely capped trigonal prism, which could be observed being gradual, as you see it with the increasing amount of gallium. And a similar type of structural transition was also observed in titanium that was alloyed with a little bit of iron, because it was really observed again that with the increasing amount of iron and increasing concentration of these icosahedral cage units tended to form at the boundary. Okay, so now we have seen a few different types of grain boundary transitions, but what is the impact on functional properties? Can we use these grain boundary transitions to design and modify functional properties? And in this regard, I would like to talk about thermoelectrics and show a couple of examples of how grain boundary phase transitions can indeed have some impact on thermoelectric properties. So when we think about thermoelectric materials, we typically want to have a high performance materials with high electrical conductivity, high Seebeck coefficient, and at the same time low thermal conductivity. And among the different types of engineering that have been done on thermoelectric material, one that's a powerful strategy is microstructure engineering. And when we introduce a high amount of grain boundaries by varying, for example, the grain size, the typical expectations is that the thermal conductivity will be suppressed with smaller grain sizes. And this is generally good for the performance. But at the same time, having a small grain size is typically associated with a reduction in the electrical conductivity. Where typically, in the case of electrically resistive grain boundaries, one observes a temperature-activated behavior. So the small grain size samples typically show a much lower electrical conductivity at low temperature compared to high temperature, where the idea is that electrons with increasing or charge carriers with increasing temperature are able more and more to overcome the barrier, the potential barrier that happens at the boundary. So this is, let's say, the general expectations when we have a variation in the grain size. But now we're thinking about grain boundary transitions, and so I would like to show you some examples of where transitions are able to cause similar changes in the properties, but without a change in the grain size. So this is really attributed to transitions. And we will see an example here from let's say, my group at the Max Planck Institute. And additionally, I would like to show another example that comes from my prior work on how we can measure the functional properties, in this case, the thermal conductivity of individual grain boundaries to try and derive some structure property relationships that link really the properties to the structural arrangement and the chemistry of the grain boundary. So let's briefly start with the first one. This case was a case of niobium iron antimony half-Voisler, where something pretty interesting was happening. So in the 5% doped case, so this niobium iron antimony was doped with titanium, and in one case, the samples were doped 5%. And when 5% doping was introduced, it was observed a behavior that was, let's say, reconducible to electrical resistance at the grain boundary. Why so? Because they noticed that upon an increase in grain size, the sample went from having a low electrical conductivity at lower temperature to having a higher electrical conductivity at the same low temperature, with the behavior, as I told you earlier, that got increasingly, let's say, suppressed as the temperature went higher. So in this case, with 5% titanium, we see a behavior that is that shows evident presence of grain boundary resistance. What was very interesting instead was that when 20% titanium was introduced as a dopant, no sign of grain boundary resistance was noticed, because the behavior of the electrical conductivity was basically the same, and the same as the, let's say, single crystal behavior, so no grain boundary activated transport, regardless of the grain size. So even by changing the grain size in the sample, the behavior was the same and not associated with grain boundary resistance. Okay, so why was this important? It was important because it was observed that this change in properties of the grain boundary was associated with a change in the grain boundary itself. And it was first observed through high-resolution TEM that the grain boundary tended to have an AB stacking compared to the ABC stacking in the grain that you can see, for example, here. And this happened in both the 5% and the 20% titanium sample. What was instead different among the two types of sample was the chemical composition that formed at the boundary. Because in the 5% titanium, the grain boundary happened to be rich in iron and antimony, whereas poor in niobium. And in the case of 20% titanium, the grain boundary happens to be also poor in niobium, but this time rich in titanium and antimony. So there was really a change in the chemical composition of the grain boundary, so a grain boundary transition, that was responsible for the change in properties that were observed. So again, in this case, the change in electrical conductivity was not related to grain size, but was related to a change in the grain boundary phase. And this can also point us to a very interesting direction, that the grain boundary phase appears to be as an additional design method for the properties themselves. I would like to spend a couple of words also on the correlation of the grain boundary structure and chemistry with individual properties for the same boundary. And so in this respect, we have been doing a little bit of work by using frequency domain thermoreflectance to achieve images of thermal conductivity with micron scale resolution. And if the grain size is significantly high, this allows to measure one grain boundary at a time. As you can see here in the first work that we have published, where individual grain boundaries in tin telluride were measured. And when we have this, let's say, images of thermal conductivity at the grain boundary, then what we do is employ a similar method of the Gibbsian interfacial excess of solute that we have seen before to derive what we call the excess thermal resistance. That is an estimate for the thermal resistance of the grain boundary. And again, to do so, we take the thermal resistivity and we integrate the local thermal resistivity minus the constant value of thermal resistivity in the grain. And by doing so, we obtain this excess thermal resistance that we can attribute to a specific boundaries, and that is our proxy, let's say, for the thermal resistance. And here I would like to show some results that we have collected on silicon. These are some of the maps of thermal conductivity that we have collected over silicon. I don't want to really you to focus too much on the details, but in general, we do see a suppression of conductivity where the grain boundary is. And in this case, I would like to focus on these two boundaries because there's a change in the resistance associated with this boundary. In particular, this one here and this one here show a higher resistance, whereas these two sides of the boundary, so this one and this other, show a lower thermal resistance. And by using high resolution methods, we could actually figure out that this was coming from a change in the structure of the boundary. So what we did was take a TEM lamella that was crossing both the boundaries, and we could observe that the side showing higher resistance was actually associated with a faceted interface, whereas the side with lowest thermal resistance was associated to a smooth morphology of the interface. So just as a summary for this work, we have seen how we can have different types of grain boundary phases and different types of grain boundary phase transitions that can occur when we have a change in the thermodynamic conditions of the system, and they can exhibit different morphology. We've seen the case of faceting-defaceting transitions, but also different structural units that could be driven by pressure, for example, but also by a change in chemistry. And then we have seen two examples. We have seen a first example in the literature of how a change in the grain boundary phase can actually have an impact on the electrical properties of a system for thermoelectric applications. And then we have seen how we can measure functional properties of individual grain boundaries, for example, via thermal conductivity imaging, and correlate this property with the structure of the same grain boundaries. So to try and develop structure property correlations. And with this, I would like to thank all the people that participated in the work. In particular, this review was from Professor Christina Scheu, Dr. Siwon Yang, and Dr. Ruben Bueno-Villoro, besides myself. And then I would like to thank all the group at the Max Planck Institute that is working on this. And then I would like to acknowledge our funding sources, in particular the DFG and the Marie Curie Fellowship that is funding my work through the project MetaSCT. And I would like to thank you for the attention. If you would like to have more details on the work, please feel free to read our article that is also linked at this QR code. And please do not hesitate to reach out for any question or comment. Thank you very much.